Okay, so welcome everyone to the next episode of the Coffee Breakdown podcast. Today's guest is Francesco Shortino, who is the co-founder and CEO of a company called Proxima Fusion, based in Munich, Germany. And so first, welcome, Francesco.
Thanks a lot. Happy to be here.
Yeah, and so I mean, we go a ways back, so we are familiar with each other, but a lot has changed since then, and now
Yep.
you're the head of this company, and there's lots of great news of you and your group and your team on the news, at least my news. So wonderful to hear you doing that.
hmm Yeah, it's been a long time since that one time in Austin when we were going around and exploring the city. I have a great memory of those days.
Yeah, me too. Crossing the river with our backpacks. That was amazing.
Yep.
Yeah, so to start us off then, Francesco, maybe you can explain what is the mission of Proxima Fusion and how do you see yourself achieving that mission through this company?
Of course, the mission is the one that everyone expects, which is to put fusion on the grid. So we do have the rather sizable ambition of building the power plants at the end of the day. And we think that there is a need for a European group to bring together an ecosystem which is much stronger than most people really fully appreciate, and to create an alternative to some of the very successful fusion companies that have been created in the United States. We think that with the know-how and the advantages that have been built with many fusion experiments, but particularly with Wendelstein 7X, or W7X for short, we can really build something exceptional here.
Okay, cool. And so how exactly do you see yourself progressing? Like, what is the role of the company? Is it constructing the device or assisting? Maybe you can enlighten us on this.
Sure. So the company is the first spin out in the history of the Max Planck Institute for Plasma Physics. That's an institute with 1,100 people, a rather sizable budget of more than 100 million euros per year. And this organization has really made the history of fusion. And as we go towards the next stage of the fusion R&D in all its complexity, I think it's clear to everyone that something is changing. Now, the idea of public-private partnerships is becoming buzzword, but it's a very important buzzword, and it actually has a lot of meaning. So as a group of people from inside the Max Planck, we saw the need and opportunity of complementing our parent institute on a path that is closer to, more focused on commercialization and on engineering. So we see a transition in stellarators more than in any other fusion approach, from research to development, from more physics to actually a focus on engineering. And we intend to be at the center of that transition. I speak of the stellarators, more particularly Proxima Fusion is focused on what are called quasi-isodynamic stellarators, or for short, QI. And these QI stellarators, you can think of them. I know that there is a breadth of different backgrounds in the audience maybe, but just to keep it short, a QI stellarator is one kind of toroidal magnetic confinement device where you optimize the magnetic configuration such that you effectively eliminate all the currents in the plasma in the toroidal direction. That sounds too simple. Of course, it's a lot more complicated than it sounds at first. So you imagine coming from your very conventional, decently well understood tokamak, where there is a lot of complexity due to the instabilities that cause disruptions, and you want to get rid of those disruptions because we have personally are of the opinion that we are neither close to solving them nor we will ever be. So we took a tokamak, and my own background was in tokamaks. Maybe we come back to this. And you start thinking about taking out the big plasma current. Once you do that, if you don't have a current, you don't have current-driven instabilities. So that sounds like a smart step. But if you take out that big current, you drive into needing a three-dimensional structure. So you get a stellarator. But even with a stellarator, you have bootstrap currents and you have Firschluter currents and all sorts of things that sound maybe nice to some tokamak folks. But in a stellarator, we really want to get rid of all toroidal currents so that if you don't have a current, you can't get any current-driven instability. We want to think about a stellarator that scales to a power plant in an extremely predictable way. We want a stellarator that works like a microwave oven, where you turn it on, it just runs, true steady state, not long pulse, true steady state, and a machine that we can predict in its most boring form of operation. So while there are questions, of course, still left on the physics of turbulence and so on, we see W7X as being a device that has showed to us how we can optimize for a number of metrics. It has been shown on W7X that once we have a design, we can actually build this stuff with extremely narrow tolerances on the engineering side. So if we now update the optimization parameters and we use what has been developed over the last 20 years, we make the QI aspect of this the center, engineering first as an approach, simulation first and engineering first. These are the two mottos of this story. Then we think we can simplify the engineering enormously. In fact, we don't just think of it, that's what we're doing. So as a company, we want to work towards a stellarator to be built likely in Munich by 2031 is our penciled in date.
Nice.
If we do that by the end of the 2030s, mid 2030s, we don't know. There is a big uncertainty as to how fast we can move. But within the 2030s, we believe that it's very reasonable to build a first-of-a-kind fusion power plant. The same that all fusion companies are, most fusion companies, not all actually, are shooting for. So we are in that very fun competition, and we think we can do it as an ecosystem before anyone else.
Wow, that's ambitious, but that's great because we need ambitious people in this field to sort of drive progress forward. I'm curious when you say power plant level. So, I mean, on the Eurofusion sort of, or at least the ITER main line, ITER itself is not power plant ready, and then it's the next one, which is demo, whatever it ends up being. So this concept you're putting together, the one that you want to aim for by the end of 2030s, is the full power plant like scale?
It's a great question. I have a very different perspective at this point, which is that if you tell me that ITER is this and demo is this, to me, this demo step, a tokamak demo step, is a story. I know that I am very well familiar with the complexity of the work that has been done on demo, but I just don't think you can build that. I mean, China is building something that looks very advanced, and you can certainly build big advanced things, but I don't believe that we can build the tokamak without disruptions. And I question whether anyone is ever going to put private funding into a thing that has the potential of making net electricity, commercially viable electricity, and has a 0.0001% chance of actually disrupting. It's not that you want the disruption probability to be small. You need it to be around zero. So the concept of what is it compared to ITER, the European demo, to me, it's very theoretical. So what I can say is our vision is to have a stellarator built in Munich that shows everything that it takes for a coherent picture of this very predictable, stable, steady state stellarator machine. If you manage to make that step and get that coherence that I think the tokamak community, not only the tokamak community, has really been looking for, I think then it will be a distant past when we thought that a tokamak really made sense. I think tokamaks are amazing research machines. That's where we've learned much of our plasma physics relevant to fusion. And they have a place in research because they're simple devices to design and relatively simple, that is, relatively simple to build, but very difficult to operate. And I think we need to take a step away from thinking as experimental physicists and think about what actually makes sense for energy markets. So then the following step in the end of the mid-end 2030s should be not enormous scale up of what's done in the first stellarator, and it should be a device that embraces the full complexity of nuclear operation. We all know that that's where stuff gets ever more complicated. So yes, that machine should be a demonstration, first of a kind fusion power plant, not necessarily connected to the grid, but it should have everything that it takes to connect to the grid.
Right. So it should be demonstrating the produce at least net thermal or net electrical energy in and out. And
the moment
That's
for our current thinking, which may evolve. I hope nobody holds me on my thinking in 2023 when I get to 2030s.
right.
Very
It's a
different.
long ways out. Yeah, I understand.
The current thinking is what we would like is
Mhm.
that the first of a kind fusion power plant does have, of course, a full blanket, of course, an advanced diverter, of course, all of these pieces that we're used to think, although not fully in an integrated way, I would say, but it also has the turbines.
Mhm.
Because that plant engineering is another one of those steps that needs to take us away from thinking as experimental physicists and realizing that some efforts are just not worth it. Some things are less likely to bring enough of a benefit compared to others. And here, actually, early conversations with what is now one of my co-founders, Jorit Leon, have been inspiring in a number of ways. So Jorit did his PhD in Greifswald, and his research has been on assessing trade-offs between physics and engineering in stellarator power plants. So he was always concentrated on the reactor, and he was developing the stellarator version of the system called Process, which has been used in tokamaks many times. And if you look at Jorit's papers, you find that some things really are more important than others, and that maybe keeping on drilling into plasma physics is it's certainly not the only thing that brings value. Of course, everyone in the world of tokamaks is well familiar that if you go from an L mode to an H mode, that factor of 2 massively changes your power plant size. Plasma physics is important and will always be, because that's what is within those magnets. But there are other things that we need to do as well. That's the role of Proxima Fusion. It's not doing physics, it's to do engineering.
Right, and it's very clear that from what you just said that motto, engineering first, is really evident in your strategy here. It's kind of looking at the system as a whole and trying to, I wouldn't say necessarily throw away, but put aside the issues that don't really mesh with an engineering solution at the moment,
And I
right?
think it would really, this message it's easy to mix up this message with physics doesn't matter. That would be a terrible message. And
Right.
for context, I did my PhD in fusion physics. I have seen the importance of doing gyrokinetic simulations and particle transport, all these things. That's the basis on top of which we have to build. There are still a lot of things that need to be improved, but we do have some very solid aspects to this. And I think realizing what is more robust than other things is part of what really makes you come forward and say, you need priorities.
Mm-hmm.
And there is a scientific effort that we need to bring forward. And I would claim Europe is at the forefront in the scientific fusion effort. We shouldn't tune it down. There is a lot more. We should bring more effort because we're evidently in the age of commercialization, or at least we have entered it. It's very early days still, a lot still to be demonstrated, but it's clear that the investors are adding funding and they shouldn't be substituting the funding that is coming from governments. So we should have physics and engineering as 2 pillars. Then there is the third pillar, which for a private company like Proxima is also fundamental, and that's commercial viability. It doesn't matter if you have the most beautiful machine on the planet, but you can't put a levelized cost of electricity estimate that is attractive. So physics, engineering, commercial viability are the things that we have written everywhere inside Proxima Fusion.
Yeah, and it's clear, like also with the concept of reliability, right? I mean, it's not just can you produce electrical energy for like an instant in time, is can you do it long enough that it makes the building of the plant commercially viable? And this is
Yeah, and obviously
definitely.
this feels like a very controversial point to bring
Mhm,
up, because there is obviously a lot of investment in concepts that don't offer that aspect of continuous operation.
mhm,
um, a lot of the latest excitement on fusion private investment has come with the NIF result, which is very exciting. And there is a lot of great physics that can be done based on those capabilities. But I do find it questionable, what does it mean for energy production? And I think my opinion there is easy to guess. We're talking
mhm.
about making an interesting performance for a very, very short amount of time in a system that would have to be scaled in a completely different way. So while I find laser fusion very interesting, I think we need to separate a little bit the energy production relevance. And I'm sure lots of people will disagree with me, and it's fine to disagree. I just want to mention the kind of stellarator power plant that we're trying to bring to reality is one where we try to focus on the highest technology readiness levels, TRLs, as they're called, and we try to work on the clearest, most robust path to fusion. We're not saying what will be a fusion power plant 100 years from now. We're saying what will be the first one, and it will not be a tokamak, in our opinion.
Fair enough. I think that with the success of W7X and, fabricating all those coils and showing that this complex geometry can not only be created, but then a plasma can be run in it. It was definitely a huge step for stellarators that definitely put them up there. So you're just building on top of that. And that's very interesting concept for sure. And
the W7X is a project that has not been fully understood by most of the community. If I look at all the variety of machines, small and large, there is a massive gap, in my opinion, between how interesting W7X is, how innovative it is, and a very distant second. And this is not to say that the work done on the machines is not important. If it trains people, and we've done measurements of plasmas, and we are advancing the whole field. But given the next opportunity to build, what is the device that has shown the biggest jump? There are things that have been done on W7X that were not necessary, you might say. I mean, what was the purpose of W7X? As I look at it, it was the demonstration that you can optimize a stellarator and build it up to specs, so to say, that you can develop the technology to meet the tolerances on W7X. There is a famous 1.5 millimeters. That was the tolerance that the big low temperature superconducting coils had to be manufactured with and then positioned, bleak positions. These capabilities had to be demonstrated. And then they chose to do it in steady state. Hopefully soon, W7X will go in 30-minute pulses, which is basically infinity, right? There is nothing special after 10 seconds, and it has already done 8 minutes. So, and then W7X was built with industrial standards, the ways we would actually build a power plant. And one may ask, why? Why are you so masochistic? And I've had the pleasure to talk and to learn from some of the people that have been there, done that. And the way I interpret their words is because that was the right thing to do to prepare for the next step. And now is the next step.
Very, very cool. And so I guess this segues very nicely into the question on what your opinion of startups like you and private investment have in bringing fusion, towards a commercial product.
I think public-private partnerships are the only reasonable way to lift off projects of this size. And every responsible player in the field needs to create a vision for what this means. How does the European fusion community, I speak of the European one because that's where I'm based, but the same applies in the US or China or wherever. How does every institution, whether new or old, how should it adapt to this new world? There is no going back. So startups have been created in greater and greater numbers, have attracted now more than $6 billion of investment. Clearly, they cannot be ignored. There are a number of companies that have more questionable methods and approaches that said, I think we need to stay away also from claiming that we are the only ones that have a good concept. There could be multiple things that work out in the long term. Mm-hmm. There needs to be a sanity check on a number of concepts, but there also, so that's what some of the more creative concept startups could say. You need new ideas. On the public side, you also need a lot of openness to different ways of working. And that openness is not as common as we may like, in my opinion. So for this to succeed, you need to identify the players that are actually listening to the academic community, giving back, being open about the physics, not necessarily about the engineering. Engineering can be a proprietary aspect on which the companies build their value, but the physics should be open. So as Proxima Fusion, we're very much in the mindset of publishing, not alone, but with the academic partners on the shoulders of which we are trying to grow this new story. That's the Max Planck, but I'm talking also about KIT and Jülich and the Eurofusion community at large. So I see it in Proxima, we see this as an ecosystem. We want to be ecosystem players, and we think that distinguishes us from some companies that go out in the dark, try something that is at relatively low technology readiness levels. It could work, but it's going to take decades more. A lot of people don't quite appreciate how long it takes to develop, to really understand the plasma physics new concept or to develop new materials. You have to stand on this really large shoulders that we've been building with public funding. And we have to create economic activity that will create opportunities for the future and create a more dynamism in our economy, and will bring taxes and jobs and all of that. All of this is possible.
Yeah, that's nice. And I think that not to make comparisons or anything, but I'm actually very happy to hear you say that CFS, the Commonwealth Fusion Systems, has sort of pledged a very similar attitude towards the physics, giving back to the community. And, it's nice to hear that.
I don't get to claim that this was a Proxima Fusion thing first. I think CFS has done that, and we consider them to be very, really great people. They have been executing their roadmap extremely well. We wish them to complete Spark and to show the world that you can get a queue of 2, 10, we'll see. We really hope that they keep working as well. And their open publications on the physics, great. I mean, that's the way. Doing otherwise would be arrogance that you can do the work that the same work that the academic community has been doing, but in a closed manner. That is just not realistic, really. So,
right. And a lot of expertise still remains in the research world, and they just have a lot of know-how from decades of working with plasmas that and even the machines themselves. What can possibly go wrong? How do you troubleshoot? How do you build?
One needs to be clear about what is the mission of the private companies and what is the mission of the public institutions. The public institutions are not there to commercialize. Most of the public institutions that we talk about are actually physics focused. That doesn't go for KIT or Jülich necessarily, but for example, it goes for the Max Planck Institute for Plasma Physics. And if you want to work on physics, your timelines don't need to reflect the ambition of building a very applied, energy relevant thing. So that's fine. I think there are multiple pieces of the story that can be more theoretical, more applied, and actually have at the one end of the spectrum, the commercial relevance. And what was particularly effective in the case of CFS, of course, was the initial partnership with MIT. MIT had a lot of willpower. I did my PhD on a significant part of my PhD at MIT was on Akato CMOD, and I've seen the last few days, I was lucky enough, and MIT had a vacuum and needed to think about, had the right people, the right energy, and the need to innovate radically. And CFS came out of the two organizations, MIT and some of its entrepreneurial spirits, really thinking, okay, what can be the path forward? In the case of Proxima, some of us have been involved in the group, have been seeing the early steps of thinking about what happens in the IPP group in Garching. And there is some thinking about upgrading aspects of grade, or maybe building accelerator there. And some of us, both in Garching and in Greifswald, and then one of my co-founders was at MIT, another one was at Google X in California. We got together and we thought, we think that that there is a different path, and that this involves public-private partnerships in a much broader way than most people have seen in Europe. But it's not entirely new. Of course, the analogy between MIT and CFS and anything that can be done in Europe, whether it's by Proxima or anyone else, it's an analogy that needs to be taken with a pinch of salt, because the US has its own system and MIT has its own flexibility, but there is a
Well,
lot
I mean,
you
this
can do.
this is a good question as well. It's like, how do you envision the feedback with the research and academic community going, right? As you say, most of your efforts now involve either engineering-based solutions or, that direction of work. And not to say engineering isn't academic, but the overlap doesn't, in my head, seem very large. So how do you see this feedback and publishing and academic work
I think
working?
the next step, if you have a physics concept that is robust, and this is something we maybe want to come back to, then you really are to realize it and focus on engineering. Now in Europe, unlike in anywhere else on the planet, we have developed industry with public funding spent on fusion more than anywhere else. This is fair to say, right? The ITER project, of course, is based in Europe with contributions in kind from every country, but Europe has put a lot of its effort. Now, ITER has been, supporting industry in a number of ways. W7X, on the other hand, has really worked with industry on some aspects that are really stellarator specific. How do you make a vacuum vessel that is curved? You have to talk to a few very specific companies. How do you make non-planar low temperature superconducting magnets? There aren't so many organizations that have ever done that. So the next steps in the engineering of a quasi-dynamic stellarator have to be taken with industry. And this industry has to be really in partnership. And this is what we're doing with, for example, Bilfinger Null is a company that was one of the two co-leaders in the construction of the W7X coils. They're based in Würzburg, which is not so far north of Munich. And it's with them that we're taking the step of working on high temperature superconductors, as one may expect. And we really knocked on the doors of many of the partners that have worked on W7X. And it's with them that we want to take the next step. In the US, there are other advantages. Here, the industry that has been working specifically on W7X is a pretty significant engineering focused advantage.
Yeah,
To
that's
speak of
also
maybe one more point, to speak of why it is important to think of engineering first in the next step. The next devices at scale, let's say pushing on performance, are going to get nastier and nastier as environments. You have to think about maintenance. You have to think about the nasty questions that are not physics questions at all. You have to think about them first. There is a really nice paper by Lutz Wegener on this, about lessons learned from W7X, from the assembly. Lutz was the head of assembly at W7X for a long time. Now he's one of the engineering advisors of Proxima Fusion. And in this paper that one can find online, he really says, well, it kind of hints we could have done some things a little different, and having an engineering mindset with a design that is not really being dictated by physics needs, but by a robust physics basis on top of which then you go and try to simplify the engineering as much as possible. Now, that was not what was done on W7X. In the next step, we believe we can build a much simpler stellarator and also a much more higher performing stellarator. And this maintenance question, for example, is one that sets much of the rest. So you have to do it at the beginning. And public institutions are not necessarily the right place to do this. This knowledge is in industry. So we have to go and talk to the right people, which we're doing.
And how does simulation play into all of this?
Great question. So the difference between a tokamak and a stellarator is that you have, at least one of the many differences, you have enormously more degrees of freedom in a stellarator. So this twisty aspect of what the magnetic cage looks like gives you so much freedom, to the point that people think about classical stellarators and optimized stellarators almost as being two different concepts. So in an optimized stellarator, to bring them up online, we really needed supercomputing in the early days. In the 90s, this could be scaled, and W7AS in Garching was one of the first optimized stellarators. Really interesting device, showed a kind of diverter, was then promising that the next stage could be even more interesting. So W7X was the result of that to a significant extent. And simulation was really central to that. Now, the kind of simulation that enabled W7X was, heavy computing at the time. Today, obviously, computing power has scaled a lot. The things that we can do today in stellarator optimization are amazing. You can consider so many more criteria, so many conflicting interests. Do you want to optimize the collisional transport of this kind, or do you want to optimize for how the diverter looks like? Or you can do lots of things. And so this brings me back to engineering in some sense. So simulation as a way to increase predictability and actually look at the trade-offs. Trade-offs is a really important word that is hard to communicate with excitement to an audience that is not technical, because trade-offs basically really means in this context that you're doing what one could call a multi-objective optimization. So an optimization in which you don't have one global optimum, you have choices. You can make your device cheaper or more robust. This is the obvious, simplest one. But you find yourself really in a high dimensional space in a stellarator where you have to be able to visualize the choices that you're making. This was the initial step that we took in Proxima. We started working on a stellarator optimization framework, building on top of open source public knowledge that has been developed over the past few years, without which none of this would have been possible. So building on top of that, we now have this framework that we call Starfinder. And Starfinder is a stellarator optimization framework that integrates physics and engineering. So including the feasibility, asking the question, is this buildable? Something that we do at the very beginning. And so everything is simulation in this. And my co-founder, Martin Kuby, who joined us, he was head of simulation in one of the Google X companies in California called Wing. He saw this story of being simulation enabled for stellarators more than for anything else. Every company can say we are AI focused, and I'm sure that's true. But in a stellarator, in an optimized stellarator, it's an entirely different beast. So you can do some things in a simulated environment or in a digital twin. You can call it whatever you want, and actually make more progress faster before you go and spend lots of money. Now, there should be no illusion that this keeps you away from hardware. Hardware needs to happen. We are working on a number of hardware demonstrations at this stage. But when you talk about the complexity of our entire device, the more predictable, the better.
Wow. That's so, as far as I understand, then in your simulation suite, that you're not just optimizing the physics, but you've included somehow considerations for the rest of the plant or other systems that is not just the plasma component. That must have been quite an effort, to be honest.
I'm not going to sell to you that this is all done.
Right.
This is what we're doing. This is what Starfinder is designed to do, from the infrastructure itself to every line of code. It's trying to do physics and engineering. And the third pillar, economic viability, always trying to keep that in mind. So you can design, just to make this slightly less fuzzy, you can think about, historically, stellarator optimization is a matter of finding the plasma boundary of the stellarator and calculating the physics, the plasma physics consequences of that boundary, you could say. The next step that you would want to do is add coils. One normally says you find coils. This is the expression that people use, meaning you find some filaments that if you run a certain current through them, then they should be producing that plasma boundary. This is often treated like a two-step process. You first find the boundary, then you look for coil shapes. The alternative, which was first brought up by Sophia Hendenberg of IPP Greifswald, is you do the two things at the same time. This is what we call single stage. And Sophia's idea has been taken to the next level at this point, because we do everything with that kind of mindset. And we don't do filaments, but we think about entire coil builds. And then we think about the support structures. And we always think about the coils allowing access to the device? Are we going to have enough space for ports? Are we leaving enough space for a blanket? There are some feasibility metrics that are more complicated than others. You can expect that this becomes at the limit of what is computationally possible. Oftentimes we try to simplify, try to come up with more and more stellarator configurations. And then fundamentally, eventually we have to throw the high fidelity modeling at a configuration. But the stellarator optimization work is about looking for using metrics that are proxies most of the time. And then afterwards, you need to still validate with the highest fidelity tools that you have. What did you find? And in all of this story, this optimization and then the post-optimization analysis, the Max Planck has played a massive role. And there are other players also across the ocean that have, it's been a very collaborative work. And now we think that the next stage is to build on top of this work in collaboration with the academic partners and add more and more engineering to that.
Okay, yeah, it sounds very impressive, and I wish you and your team a lot of luck in it. I want to switch gears a little bit to the more personal side. Of course, I met you and I knew you when you were, a researcher in training, more or less, and so you've been very focused on the scientific aspects, the physics components, and maybe a little bit of the engineering. I'm not too certain, but now you've completely switched gears. You're, co-founder of this company. You probably have a lot of more business-like meetings or more, investor type shareholder stuff, and then engineering stuff as well. So like, how do you find that? How was that transition for you? What caused you to want to do this?
Difficult question to answer, of course. I would say that what caused me to do it was the need to do it. Somebody to do it. This is the way we looked at it as a co-founding team. We said there is a hole, nobody's moving, and somebody needs to break things. And so we tried to do it with the most delicate way that we could. We wanted to be ecosystem players from the very beginning. We said we do not believe that this can be done in isolation. This has to be done together, and we want to do it together. So we took care of that. We tried to give the right signals from day one. We were always happy when somebody really understood the good intention. And then, when jumping from a research-focused environment so I was working on core transport, then divertor modeling, was in diagnostics and data analysis and so on. Then at some point, I was one of the Eurofusion coordinators for negative triangularity tokamaks, and that maybe helped me also look a bit at the bigger picture. Do these advanced scenarios answer the critical questions? I wasn't so happy with the answer that I was giving myself. So I started looking a little broader, and I had somebody who was very patient to explain to me what is the promise of stellarators that I hadn't quite fully understood entirely. So my transition was about trying to look at a bigger picture. And now that's all I do in some sense. So it's a lot of personal relations. It's a lot of communication about priorities. There is a lot that both myself and my co-founder Lucio together, we've been working on the fundraising, and we have a number of other team members that have been involved on the creation of the company, the co-founders, Jonathan, Jorit, Martin, but then also a wider co-founding team with Leonard, Andrea, and Jimmy. With all these people, when you create a startup, you put everything on the table, all you have, and then you figure it out. And that is the startup vibe. It's the startup superpower. It's the power where you don't say, sorry, but that's not in my job description, or, but I wasn't trained to do that, or my supervisor didn't tell me to do that. It's you go in and you get it done, and you set a standard for quality and a standard for speed. And this was inherent, I would say, to some of us, as people that jump in a startup, you need to want that speed, that energy. And in some sense, I feel like that wasn't a real big transition for me. I've been working like that for a while. I don't work more now than I did while I was doing my PhD, postdoc, or whatever. But now it's broader in some sense. It's less focused what I do on a specific code. I enjoy hearing about the technical progress from my team. It's amazing how when you put enough smart people on the same task and you don't see them working individually, but as a team, you can get stuff done at a crazy speed. So this is wonderful for me to see and for me to be embedded in. It's not my main contribution to the company, but that's the beauty of a company is working as a team.
Yeah, it must be a wonderful, enriching learning experience for you, also tackling on projects of different nature and, learning what's involved in different worlds than just the scientific and one small region of physics.
That's right. So then on the more entrepreneurial side, both Lucio and myself have been involved in entrepreneurship courses. Lucio actually took a master of global affairs for 1 year, and one of the critical things in creating a startup is to know what you don't know and surround yourself with mentors and with people that can advise you. Being a first-time founder, it means that every time you get onto a new problem, it's a problem that you can't pull from the drawer a solution that you used the previous time. But if you surround yourself with people that are willing to go the extra mile for you, you can go much faster. And this has been really one of the transformational things for us. 6 months into, we moved the team to Munich we started full speed on April 17th of this year. 6 months afterwards, I think we are further than we dreamt of. And even our choices of who to fundraise with. So when you go out and fundraise, if everything is going well, you have multiple offers from multiple investors, and then you have to make a decision, and it can be made based on your sense of what your guts are telling you, or you can have a strategy. Our choice has been to work with investors that are very operational, people that actually get in the trenches with you and actually do things for you. This is becoming more common among early stage investors, but we think we got some pretty amazing human beings that you need to do the beer test, as somebody from one of the founders of Lilium, a really successful company here in Munich. He told me, you want with new team members, or also for the investors, I would extrapolate, do the beer test. Would you like to go for it? And I think I'm very happy with the drinks I've been having with. They are exceptional people, and they've been helping us a lot.
Okay, yeah, that's super cool. I think maybe a question which is going to be a bit added value to our listeners as well is a bit of advice. Do you have any advice for how to do that? Like how to identify people who will help you? How do you get in touch with them? How do you, be involved with them? Is it just going up and saying hi, or is there more to it?
I think saying hi is a good start.
Right.
Not thinking that others necessarily know that much more than you do. You have, especially if you're in fusion and you've spent your PhD doing something specific, you should know that you are qualified to have a say, not on the whole fusion story or something, but you have your path, and somebody else may want to listen to you as well. The other side is, of course, modesty, and being humble is important. When you go and meet somebody that has an impressive track record, just ask questions, listen. And I think this is a skill that I've been training more and more, because it's important to realize what you don't know.
And how do you identify these people? Is it just blanket, talk to as many people as you can, or is there
not as many as possible? So it depends what you're looking for. Pick your metrics, I would say. So decide what are you actually looking for, and then brainstorming who could be my dream people to talk to. If you create a first connection, ask that connection to make another connection. So ask for a warm introduction. That can really help sometimes. But it turns out that I think most people, when we talk about fusion and in Proxima, our experience has been that pretty much everyone wants to have a chat with us. It's very interesting, objectively. Maybe not everyone is ready to put their life savings into fusion, but is interesting. Turns out that if we write to somebody, they will get back to us. Now, we have an interesting story, an interesting company. I understand this is not the same as if you do something as an individual. But if you as an individual are interested in spinning out a company about some instrument that you developed in the lab, or about you think that a certain code can be brought into a software that can be commercial, not what I do, not what I have direct experience with. But
Right.
I think generally, especially in Europe, we need to have more of we need to fight the risk aversion and wanting lots of security and safety. The world of jumping into startups involves getting out there, putting your face to it. Some people won't like it, so be it. As long as your integrity is with you, go for it. That would be my main advice to anyone who's anywhere close to interested in this stuff. If you want to join a startup, go for it. Send them a message. Send us a message. We'd be happy to hear from people of very different backgrounds. And if you want to go and do something else, just break your uncertainties and give it a shot.
Okay. Wow. That's actually a very strong message. So how about we leave it on that, Francesco? Thank you very much for coming onto the podcast. It was a pleasure speaking to you again. And wish you good luck with your company. And I'm looking forward to hearing all the great news about your successes.
So we'll be in touch.
Absolutely. Thanks again.
Bye.
Bye.